Good morning, everyone. So today we're going to start looking at systems of linear equations. So when I say a system of equations, basically this means we're looking at multiple equations and trying to solve them simultaneously. So with a 2 by 2 system of linear equations, what that means is that we have two equations and two variables that we're trying to solve for. Later on in this unit, we're going to look at 3 by 3 systems of linear equations, and that just means three equations and three variables. So we're going to look at three different ways that we can solve these 2 by 2 systems. The first way is going to be by graphing the functions. Then we're going to look at something called substitution. And then the last way we're going to look at is elimination. So we're going to go through all of these different techniques in this video to solve these systems. Okay, so let's go ahead and try solving them by graphing first. So we have on this one two equations, all right? This is our system right here. Y equals negative x plus 6 and y equals x minus 4. So when we solve by graphing, we're going to start by just plotting both of these equations. I'm going to go ahead and just label these equations 1 and 2 to start with, just so that it's easier to talk about them, okay? Now also I want you guys to recall that when we're talking about the equation of a line, we're looking at y equals mx plus b as the slope-intercept form of a line. Our slope, remember, is m. Okay, that's our slope. And with that, we're thinking rise over run. So the change in y over the change in x. And then b is our y-intercept. So let's just identify the pieces in both of these equations. Okay, so equation 1, we have y equals negative x plus 6. So even though it's not written here, we have an understood negative 1 as our coefficient on the x. So that's going to make that our slope. And with slope, you always want to think of it as a fraction, rise over run. So this would just be negative 1 over 1. Okay. Our b value is 6, which means that our y-intercept is the 0.06. Okay, so let's go ahead and let's graph this line. So when you're graphing the equation of a line, remember you start with the y-intercept. So in this case, we're starting with our y-intercept at 0.6. And then we use the slope to just count. So our rise over run is negative 1 over 1, which means from our starting point right here, I'm just going to go down 1, right 1, and plot another point. Now, really all you need to graph a line is 2 points, so you could just go from there. If you want to get a couple more points on here just so that it's easier to draw that line, you can. And we would just keep doing the same thing. So from that point, I'm just going to go down 1 over 1, plot a point. Down 1 over 1, plot a point. Okay, and you can do that for as many points as you want to. I'm going to go ahead and just connect my points here. And I've got my first line. Okay, so that is our y equals negative x plus 6. Okay, so now let's go ahead and do the same thing with the other line. So for number 2, we have y equals x minus 4. So again, identify our slope, which is that understood 1 out front. So again, if you think of it as a fraction, that's just 1 over 1. Our b value is a negative 4, which means our y-intercept is at the point 0, negative 4. All right, and let's again go ahead and graph this. So starting with our y-intercept at 0, negative 4, and then our slope on this one is 1. So from our first point, we're going to go up 1 over 1 and plot another point. And again, if you want to keep going to get a few more points on here, you absolutely can, but really all you need to graph a line is those 2 points. I'm going to go ahead and just connect my points on this one. If you have a ruler or something, that might make it a little bit easier. But if you're good at just eyeballing a straight line, then you can just draw it right in. Okay, all right, so there's our graphs, okay? All right, so now that we have this graph, remember our goal here is to solve the system. So when you're graphing a system of linear equations, the solution to your system is going to be the intersection of your two lines. So in this case, if we look at this graph right here and we look for where our graphs intersect one another, because that's where they're going to be equal to one another, that's why that's solving our equation, is at this point right here at 5, 1. Okay, so that is the solution to our system. Okay. All right, so this is the basic idea of solving with graphing. Now, the only thing that you might run into as you're going through these problems is these equations already started in our slope-intercept form. They were already y equals our mx plus b. So if you wanted to solve a system by graphing, but your equations weren't already solved for y, you would need to just rearrange them first, put them in that slope-intercept form, and then you could graph them and go from there. Okay. All right, now this equation, or this system in particular, worked really nicely for graphing because we happened to come up with a solution that was a nice point, that 5, 1. Both of our x and y values were whole numbers. It was easy to see. But of course, we're not always going to have nice whole numbers as our answers. And so if you're trying to solve by graphing and your solution is a fraction, maybe you have a 1/3, well, that's a little bit harder to just eyeball when you're looking at the graph. So we also want to have some algebraic ways of solving these systems as well. So the next way we're going to look at is using substitution. Now, the basic idea here is we have our two equations. We're going to start by taking one of the equations and solving it for either x or y. It doesn't matter which variable you solve for. Typically, I would say solve for the one that's easier if one of them looks easier, okay? So take one of the equations and solve it for either x or y, okay? From there, we take that equation and we substitute it into the other equation. What this does is it gives us an equation in terms of just one variable instead of two. Then we'll solve it, and then after that we do this back substitution step where we basically plug it back in to find the other variable. Okay, so let's go through and let's try this process. So again, the first thing we do is we solve for one of the variables in either one of the equations. So I'm going to go ahead and just label these again so that they're a little bit easier to talk about. Okay. Okay, now it does not matter which equation we're looking at or which variable we solve for. Okay, you can go either way. So just for simplicity, I'm going to start with equation 1, which is our 5x minus y equals -3. And on this one, it looks like it's going to be easier to solve for y. Now, the reason why I say that is because the x has this coefficient of 5, which means we would have to divide by a 5 in order to solve it, and we'd end up with some fractions. Whereas the y, it just has that coefficient of -1, so we'll have easier numbers to work with. So I'm going to go ahead and solve this for y. So I'm going to subtract my 5x over, and then divide the whole thing through by a -1, which will give me y is equal to 5x plus 3. Okay, so we've solved the first equation for y. Okay, so that's step 1 right here. Solve for one variable. Okay, so then after we do that, this is where we substitute. So we take this equation, the y equals 5x plus 3, and we substitute it into the second equation. Okay, it's always important that you substitute into the other equation. Okay, it's not going to do you any good to substitute it back into itself. Now, what I mean by this is just in place of the y right here, we're going to substitute in 5x plus 3. All right, so this is our substitute step. So we'll have 2x minus, I'm just going to put it all in parentheses, and in place of my y, I'm just substituting in the 5x plus 3. And that's equal to 1. So we just substituted into our second equation. Okay. All right, so now we just need to solve for x. So I'm going to go ahead and distribute my negative in here. So 2x minus 5x minus 3 is equal to 1. And then just continue simplifying, so we can combine our like terms here. 2x minus 5x is a negative 3x. And I'm going to go ahead and add this 3 over to the other side. If we add that over, we would get a 4. And then just divide by the negative 3. So we come out with x is equal to negative 4/3. Okay, so we've solved for one of our variables. Okay, so the last step then is to back substitute. So on this step, we're just taking what we just found for x and substituting it back into our equation that we found in the first step in order to solve for y. Okay, this is my back substitute step. And just plugging it back in to solve for your other variable. Okay, so we would have y is equal to 5 times negative 4/3 plus 3. Okay, so 5 times negative 4/3 would be a negative 20/3. And then if we got a common denominator, our 3 would be 9/3. So negative 20/3 plus 9/3 is going to be a negative 11/3. Okay. And then the last step is just to write your solution as an ordered pair. So you want to write it as an xy. So in this case, our x value we found was negative 4/3, and our y value was negative 11/3. So that is our solution. All right, so this is the basic idea with the substitution method. So again, what we did here is we started off, we took our first equation, solved it for y, substituted that into the second equation so that we were able to get our x value, and then plugged that back in to solve for our y. Okay, so let's go ahead and look at a second example. All right, so same idea on this one. I'm going to start by just labeling my equations as 1 and 2. All right, and we want to solve either one of the equations for either x or y. This time, the second equation looks a little bit easier because there's no coefficients on the x's and y's. So I'm going to take equation 2. And we can solve it for either variable. I'll mix it up a little bit this time. I'll solve for x. So we need to add the y over, and then divide through by a negative 1. And we've isolated our x. Okay. All right, from here, we need to substitute. So we're going to substitute this back into the first equation, okay, because this was equation 2. So we need to substitute it back into equation 1. And just for our x, we're going to plug in negative y minus 5. So we have 4, and then times negative y minus 5 plus 4y is equal to negative 20. All right, distribute our 4 in. We have a negative 4y minus 20 plus 4y is equal to negative 20. Now you might notice here, if we combine our like terms, we have a negative 4y and a positive 4y. So if we combine those, they just cancel each other out. And we're left with negative 20 is equal to negative 20. Well, notice that all of our variables are gone. Okay, we don't have any x's or y's left in this equation. We're just left with this statement here that negative 20 equals negative 20. And if you think about that, that's always going to be a true statement. No matter what x and y are, -20 always equals itself. It always equals -20. So because this statement is always true, what this means is that there are infinitely many solutions to the system of equations. That's how we say this. There are infinitely many solutions. Okay. Now I'm just going to warn you guys that the textbook is going to write these answers a little bit differently. Whenever they have infinitely many solutions, they sort of write their answer with variables in them. They write an expression of like how x relates to y. You do not need to do that, okay? Just anytime you see something like this where you have no variables left over and the same number on both sides of the equation, you can just say infinitely many solutions, okay? All right, guys, I think I'm actually going to end this video here. We still have one more way that we have to look at solving equations or solving these systems. So in the next video, we're going to look at solving using elimination. So keep watching to see more techniques for solving these 2 by 2 systems.